Okay, so here they've given us a formula for a conservative force, and they're asking us to find the potential energy at a certain location. So the key to this is the definition of, well, it's really the definition of change in potential energy, and that's equal to the negative of the work done by a conservative force. So in this situation, we're going to take the final potential energy minus the original potential energy is equal to the negative of the work done by the conservative force. And since this force varies with position, you put in different x's, you get different forces. The only way to do this is through integration. So we're going to do the integral of the equation, negative 3x minus 5x squared dx. And they're interested in the potential energy when the object is at 2 meters. Since they told us that the potential energy is equal to 0 when it's at the origin, I'm going to make my starting position the origin. That way, I can automatically say that at the origin, in other words, where the initial potential energy is, I can put a 0 there. While we're at it, why don't we just carry through this negative sign? So negative, negative, negative could be positive, positive, positive. That'll make the math a little bit easier. All right, so we're going to end up with UF is equal to, now let me integrate this. So x to the next higher power would be x squared. Divide by the new power, so 3/2 x squared, 5/3 x cubed plus c, and we're going to integrate from 0 to 2. And when we do that, looks like this, 3/2 2 squared plus 5/3 2 cubed plus c minus, well, it's minus 0 plus c. I think you'll see that in the math. So in the end, the answer that I got was 19.3 joules. So that's the potential energy at that location. That's the answer to A. Okay, how about B? Question B says that we are to find the speed when it passes through the origin, and they give us its speed at a different location. Well, this sounds like ukwuk to me. U at A plus K at A plus W and C equals U at B plus K at B. And here, see what we're going to put in for the potential energy. What we have right in here is an equation for the potential energy. So whatever location we're interested in finding the potential energy, we can just put our x values into that equation. So let's say that A is when it's at x equals 5 meters, and let's say that B is at the origin, where x equals 0 meters. So at A, I'm going to use the potential energy equation that we got up here and say 3/2 x squared. Whoops, I wanted to put in that 5. 3/2 times 5 squared plus 5/3 times 5 cubed plus c. That's the potential energy at A. And what about the kinetic energy there? Well, it's 1/2 times 20, and they told us its velocity was 4 meters per second. Doesn't matter what the direction is because it's going to get squared anyway, so 4 squared. No non-conservative forces, so I'm going to put in a 0 for that. And then the potential at B, I mean really the potential at B is just this piece right here. And so that's 0 plus c. And then the kinetic energy at B is 1/2 m is 20 times the speed at B squared. And so you've got a c on both sides of the equation, but that'll cancel out. And you can do the rest of the math and find out that the speed at B is equal to 6.37 meters per second. Okay, now we get a little bit more theoretical with part C, which says what are the answers to A and B if the potential energy of the system is taken to be negative 8 joules when the object is at x equals 0. Well, all that really does is change this formula up here a little bit. Let me rewrite that. So now we're saying that at x equals 0, the potential energy wasn't 0, it was negative 8. Well, the other side of the equation is still true. When you integrate the other side of the equation, you're still going to get 3/2 x squared plus 5/3 x cubed plus c. You're still going to get that. And we can still evaluate that from 0 to 2. And we're still going to get 19.3, except now the other side of the equation says UF plus 8. So if we really want to get the potential energy at that location, now it's off by 8. Now it would be 11.3 joules. So that's the answer to that question. And then they ask us about the speed. Well, what I want you to notice right here, maybe even better to look at the equation above, that the potential energy, we were finding the potential energy earlier by using this part of the equation, 3/2 x squared plus 5/3 x cubed plus c. That was really our formula for potential energy. Well, now that's equal to final potential energy plus 8. So really now potential energy is equal to this same equation here minus 8. And so I can adjust the UCWUC equation that I used earlier by just putting a minus 8 on this side. And of course I'd have to then put a minus 8 on that side, and they would cancel out, and we would get exactly the same answer. So this is a good example of how it really is changes in potential energy that matter. That's why it's defined as change in potential energy equals the negative of the work divided by conservative force. Actual values of potential energy do not matter. It's only how much the potential energy changes that matters, because if the potential energy gets smaller, that allows that much energy to go into kinetic. If the potential energy gets larger, it has to take that much energy from the kinetic. So it's only the changes in potential energy that matter.